Question number 11 says a satellite of mass 100 kg moves from a point where the gravitational potential is minus 10 megajoule per kg to another point where the gravitational potential is minus 80 megajoule per kg. Then during the change in position, the satellite moves. These are four options. Now see, what is the first gravitational potential? That is given equal to minus 10 megajoule per kg, and the potential gravitational of another point is equal to minus 80 megajoule per kg. And see, this value is lower. So it is moving from higher value to the lower value. So there is decrease in potential. Now you have to find whether it is coming closer to the earth or away. See, where potential falls, it is coming closer to the earth. And what is the change in potential energy? And change in potential energy is equal to change of potential multiplied by mass you move. And see, the final potential is 80 megajoule. The initial potential was minus 10, and mega mean 10 is power 6, and mass is equal to 100 kg. So this will be decrease in potential energy. So 80 minus this is equal to 70 into 10 is power 6 into 10 is power 2. So that become minus 7000 into 10 is power 6 joule, and that is called minus 7000 megajoule. So decrease in potential of energy of minus 7000 megajoule, and it is coming closer to the earth. So answer to this question is the fourth option. The question number 12 says that a light rod of length 80 centimeter is suspended from the ceiling horizontally by means of two vertical wires of equal length tied to the ends of the rod. One of the wire is of steel and the area of cross section is given 0.1 centimeter square, and other is of brass of area 0.2 centimeter square. Then the position from the steel wire along the rod where the load should be placed to produce equal strain, and given that Young's modulus steel is twice that of Young's modulus of the second rod B. B might be the brass. Now see the diagram. This was the case. These are two strings. A very light rod is this one, has no weight. This is for steel and this could be for the brass. Now somewhere I am placing here the weight W at the distance of say x. This will be the remaining distance, which is equal to L minus x, and this distance would be 80 minus x in centimeter, because total separation is given 80 centimeter in the question. Now he says that the strain should be equal, and you know that the force per unit area is equal to Young's modulus into the strain. If I write the strain delta L by L, that is equal to F upon YA. And he says that strain and both are equal in the steel is equal to the strain in the brass wire. Now Y of the steel is given 2 times the Y of brass, and area is given 0.1 centimeter square, and for the brass this is YB and area is given 0.2 centimeter square. We can convert, and you find that Fs is equal to Fb. That means both the tension or both the forces are equal. F steel and F brass. Now we want to find out the position from here. So for the position we'll take the torque about this point, about the load. So let's take the torque, but the load should be 0, and this torque means Fs multiplied by the distance x. This is producing the clockwise, and that should be the equal to anti-clockwise, that is equal to Fb multiplied by 80 minus x. But Fv was equal to Fs, so I can replace by this. So Fv into x is equal to Fv into 80 minus x. Therefore this cancel out, and 2x is equal to 80, so x is equal to 40 centimeter. So that's the answer. So option is 80 centimeter. The answer to this question is option number 2. The question number 13 says that a light beam incident from air to the glass slab at Brewster's angle, as shown in the figure, is a Polaroid is placed in the path of emergent ray at the point P and rotated about an axis passing through the center and perpendicular to the plane of the Polaroid. Then, these are four options. Now, dear student, let's say this is unpolarized light. So, as unpolarized light hits this one at Brewster angle, so this light is plane polarized, but this light is partially polarized. So, as this light comes out, so it's partially polarized. That means it has the component even in the direction of perpendicular to this plane outward. So when you place a crystal somewhere here and you rotate the crystal, what will happen? When you are in front of this component, so intensity is continuously decreasing, but because of the second component, the intensity is always present. So intensity will become minimum but not zero. That is only true when it is fully polarized, but it is partially polarized. Therefore, in partial polarized, you'll get some intensity even at the minima, even at the rotation. So intensity of light as in the Polaroid should go through minimum but not zero for one orientation of the Polaroid. So the correct option to this is that intensity of light as seen through the Polaroid shall go through the minimum but not zero on two orientation of the Polaroids. So answer to this question is 3. The question number 14 is that the correct graph showing the variation of decay constant with number of active nuclei dN by dt versus this swectivity, you know that dN by dt, and that is proportional to n, and dN by dt is equal to minus because it is decaying into n. And see, dN by dt is on y-axis and this is certain constant minus lambda into n, just like m into x. So m is a negative, so slope is negative and y is equal to mx, a straight line with negative slope passing through origin. And look at the graph too is y is equal to minus m into x. So this, the true relation to this is option number 2. The question number 15 is which of the following is not true for nuclear forces? Nuclear forces, first is saturated forces. Yes, their interaction remains within 1 to 1. It is charge independent, that's true. It's a spin dependent, that's true. It is only attractive. No, nuclear forces, when the distance between two nucleon becomes less than 0.8 femtometer for me, then the forces become repulsive. So to answer this question is option number 4.